Hi, good morning students. Welcome to this video where we'll be going through the TYS series topic on chapter 15, Rate of Reactions. Now, before I go on further, I would just like to highlight that I'll be going through the corrections from the structured questions first, then after that we will come back to the multiple choice answers. Alright, so let's get started. Now, in terms of the structured questions, you'll notice that for this particular chapter, there's quite a bit of explanation on how does the changes in terms of things like concentration, particle size, or even temperature affect the rate of reaction. So this chapter actually emphasizes a lot on explanation, and as a student, when I explain the concept, just take note that we are actually supposed to use what we call the collision theory, which is our effective collision concept. So what do I mean by that? Now, in every reaction, for the reaction to happen, there must be this thing called effective collision. And then, how will we know that there's a faster rate or slower rate? That's when we talk about this concept called frequency of effective collision. Let's take question 1 for instance. Right, question 1 is talking about how these chemicals of gases actually do not react together under normal conditions in the atmosphere. However, in a car engine, the gases actually react to form your nitrogen monoxide. Then you're asked to use ideas about energy and collisions to explain why. Now, take note that for this question, you're supposed to use ideas about energy, right? Not about pressure, not about other chemicals and whatnot. But you're supposed to focus on the energy of the particles. And we know that in a car engine, temperatures get very, very hot. Now, what happens when temperature gets hot? That's when your particles start to gain kinetic energy and they start to move faster. Now, when this happens, right, there will now be more particles with energy greater or equal to activation energy. And then this actually increases the overall frequency of effective collision, hence resulting in a faster rate of reaction. Now, as we're going through this particular question, you'll notice that quite a number of times students will actually miss out on point number 2, right? So what exactly do we mean by more particles with energy greater or equals to activation energy? Let's take a look at this video to have a better understanding. Now, as you watch the video, do take note that this concept that will be shared is actually a junior college concept or that you learn in A-level, or if you go on to take chemistry in polytechnic, right? But it helps to help you understand what exactly do we mean when we say that there will now be more particles with energy greater or equals to activation energy.
Hi and welcome back to Free Science Lessons. By the end of this video, you should be able to describe the Maxwell-Boltzmann curve of particle energies. You should then be able to use the Maxwell-Boltzmann curve to explain the effect of temperature and catalysts on the rate of chemical reactions. Over the last few videos, we've been looking at the rate of chemical reactions. We've seen that in order for a reaction to take place, the reactant molecules must collide with enough energy to start breaking chemical bonds, and scientists call this the activation energy. Now, if we measure the energy of all the molecules in a gas, a liquid, or a solution, we get the curve I'm showing you here. This curve is called the Maxwell-Boltzmann distribution. There are several important points about this that you need to learn. Firstly, the curve starts at 0, 0, in other words, the origin. What this means is that there are no molecules with zero energy. Secondly, some molecules have a very high energy. In fact, the curve does not touch the x-axis at high energies. So this tells us that there's no maximum energy that molecules could have. And lastly, the area under the curve tells us the total number of molecules in the system. Okay, now I'm showing the activation energy for a particular reaction. Remember that in order to collide effectively and react, molecules must have at least this energy. These molecules are represented by the area under the curve to the right of the activation energy, and I'm showing that in green. Now, another way to increase the rate of reaction is to increase the temperature. I'm showing you here the effect of increasing temperature on the Maxwell-Boltzmann distribution curve. Here, T2 represents a higher temperature than T1. You'll notice that at higher temperatures, there are more particles with very high energies. We can also see that the most probable energy increases, but the number of particles with the most probable energy falls. Students sometimes find this idea challenging. You need to remember that the area under the curve represents the total number of molecules. We have not changed the number of molecules, we've only increased the temperature. So the area under the curve cannot change when we increase the temperature. Therefore, at higher temperatures, the curve shifts to the right, but the height of the peak falls. Now, there are two effects to increasing the temperature. Firstly, the molecules are moving faster, so the frequency of all collisions increases. Secondly, at higher temperatures, we can see that the number of molecules with at least the activation energy has increased substantially. And again, I'm showing that in green. So now, a much greater proportion of the collisions are effective and result in a reaction. And this increase in effective collisions explains why the rate of reaction increases at higher temperatures.
Now, having watched the video, I hope you now take note of how to use this phrasing to explain the concept. Let's go on to take a look at the second question. Now, the second question talks about this concept of ozone breaking down, and we have learned this actually in the earlier chapter on air atmosphere. But I think what is interesting about this question is what do they actually mean by this concept of overall equation. Now, overall equation in terms of chemistry, what we can do is actually to look at the equation in terms of the left-hand side as well as the right-hand side. Now, we know that every equation has a left-hand side with an arrow towards the right-hand side, right? So when we talk about overall equation, what we really want the students to do is to take all the things on the left-hand side, put them all together in a mega equation here on the left-hand side. Then take everything on the right-hand side and put them all together on the right-hand side in a mega equation over there. Then start looking at what has been repeated on the left and right. So for instance, chlorine, for instance, this ClO molecule. And then you'll be left with the final equation. So what exactly is happening over here is we're actually getting students to combine the two equations together. And how do we combine it? We take all the left-hand side together first. Then we take all the right-hand side together on the right-hand side. Then we start to strike out things that are being repeated because there will be some molecules that will be repeated. Okay, so that helps explain what this question is talking about. Now, how does this whole question actually help us to understand how chlorine is acting as a catalyst? Now, you should know that in terms of definition of a catalyst actually lowers the activation energy required for the reaction to happen, but more importantly, they remain what we call chemically unchanged at the reaction. So if you look at the equation above, right, what you'll notice is that the chlorine, which is the Cl, using this pink highlighter over here, what it did at the start was it reacted with ozone. In the process, it actually broke down one of the ozone into O2, and in the process it formed this other chemical. Then this other chemical actually went on to break down another ozone to, this time around, 2 oxygen, and in the process the chlorine forms it again. Now what this means is that this chlorine is essentially regenerated in the whole reaction. If you take note, in the first equation it was used, in the second equation it came out. This is what we call a chemically unchanged substance. So what did the chlorine do over here? It actually causes the reactions to start. And once the reaction starts, itself is formed again. And what happens is that it will then go and find another ozone and repeat the same thing over and over and over again. That is essentially how it's working over here as a catalyst, right? It gets regenerated, it breaks down another ozone over and over again until the whole ozone layer is broken down. So how do we explain about that portion? We will mention that, first and foremost, we know that the chlorine is actually breaking down the ozone, but more importantly, it remains chemically unchanged at the end of the reaction. And that is the concept of what a catalyst is. And of course, how are catalysts actually useful to us, right? Catalysts are useful because they actually help to reduce causes, like what is mentioned in this question itself, right? And how does it reduce cost? First and foremost, because they are chemically unchanged, right? That means you can actually reuse them over and over again. And this actually cuts down cost because you don't need to get new catalysts. You can always, it will be regenerated in the process and then you can use it again for the reaction once more. Secondly, we know that catalysts, how they work is that they will actually speed up the reaction, right? And with speed up reaction, what it means is that from a manufacturer's point of view, or from someone that is operating a major big reaction in the industry, you actually requires less energy to speed up any form of reaction. If you think about it, we learn about things like Haber process, we learn about different reactions that's going on, and often we need to supply heat, right? But with a catalyst, what it means is that the reaction will be a lot faster and there's no longer such an important need for you to supply heat anymore. And that's why the reaction can actually take place at a lower cost. Right? So this will help to answer for this first page of the structure questions. Let's go to the second page. In the second page, it was mentioned about this reaction between dilute hydrochloric acid as well as dilute hydrochloric acid with metal oxides. Then as students, you are being asked to think of how are these two reactions actually similar. Now, just a quick recap, we learned in the acids chapter that this is essentially a reaction between acids and metal oxides, which are our bases. Right? So what are your acids-base reaction? It's called neutralization. But more importantly, what is similar, we always talk about chemical processes, right? It's the product. Right, so in this case, you actually produce salt and water only as a chemical. Secondly, you are asked to think of why exactly is the rate of reaction for dilute ethanol acid actually slower than that of hydrochloric acid, even though they are the same concentration and same temperature. Now, most of us here will remember that actually hydrochloric acid is a stronger acid, right? And if it's a stronger acid, what happens is that you will dissociate completely to form a higher concentration of H+ ions. This is where we link back to the concept on how concentration affects the number of reactant particles per unit volume. And once that you have a high concentration, it means that you have higher number of reactant particles per unit volume, and that will automatically increase the frequency of effective collision, and therefore the rate of reaction will speed up. Yep. So this is a question that actually joins the concept of acid together with the concept of rate of reaction together. Moving on to the next question, whereby the next question actually connects the chapter on chemical energetics with the chapter on rate of reaction, right? So you are being told that there's this process that's endothermic, right? And this endothermic can actually be catalyzed using a catalyst, and you are asked to draw the reaction that is uncatalyzed as well as the reaction that is being catalyzed in terms of the energy profile diagram, right? So you recall from the chapter on chemical energetics, the energy profile diagram is the one that has a mountain, right, before it changes to either the reactant or product level. So in this case, because it's endothermic, what we do know is that the energy of the reactant and the energy of product must be in this level so that there is actually an overall gain absorbed in energy from the surrounding. So enthalpy change is actually positive, right? So this is what we know from the concept of endothermic. Now, what would a catalyzed and an uncatalyzed reaction look like? Take note that an uncatalyzed reaction would be saying that you actually start from the reactants, you rise all the way up to the peak, then you come back down to the products level. This is your endothermic curve if there's no catalyst. And what is the activation energy? Take note that activation energy would always start from where the reactant is. Right? So in this case, the reactant is over here, and the activation energy should move all the way upwards until the peak of the mountain. Right? This is where your dotted line must come in to help the examiner know where exactly are you tracing the arrows from, so that you won't be penalized even though your drawing may not be as clear cut as what you want. Right? So use your dotted line there to guide you in terms of where should your arrow end up with. So I repeat, activation energy must start from the reactants level, and in this case, it will spike all the way to the top of the mountain. So this is the activation energy of the uncatalyzed reaction. When there's a catalyst, that means when you put in a catalyst now, the reaction should now have a lower activation energy. That's where your mountain, the peak of it, will actually fall lower. So I'm using a dotted line here to represent or the yellow highlighted line to represent the catalyzed reaction. This time around, your activation energy similarly will start from where the reactant is, but it will peak at the lower mountain. And this is your activation energy of catalyzed reaction. Okay, so this is actually how we go about drawing the endothermic process energy profile diagram in terms of whether there is no catalyst or when there is a catalyst. Okay, so that's for your second page of the structured questions. Let's move on to take a look at the third page of the structured questions. Now, the third page is where we start to go into the free response questions, right? Where it gets a bit more tedious, there's more data, and we need to see what exactly is going on. So for this first question here, it's talking about this process called the iodine clot reaction. And this iodine clot reaction, how it works is that we actually look at when the saturation turns blue-black, right? And that's when there's a certain amount of iodide that's being produced. This particular experiment, you'll notice that concentration of iodide ions is being investigated, temperature is also being investigated, and catalyst is also being investigated. And then they actually measure the time taken for the blue-black color to appear. Okay, just to make sure that we're all on the same page, this one, because it takes the shortest amount of time, it is the fastest. Okay, this one, because it takes the longest amount of time, it is the slowest. Do take note that time and rate are inverse. So the first question asks students to think of which experiment is actually used as a reference for you to compare the effect of the variables. Now, what do you mean by reference to compare the effect of the variables? Essentially, what this means is that this experiment has a variable that is changed as compared to another experiment. So basically, we are trying to see, is there an experiment out of these four that has one variable being changed as is compared to the other experiments. And if you take a look at it, for instance, right, if you look at experiment 1, the concentration used is 0.1, temperature used is 20, catalyst, there's no catalyst, right? If you compare experiment 1 as a reference to experiment 2, you can say that, oh, yes, the concentration did change from 0.1 to 0.2. Then let's take a look at what if you take experiment 1 as a reference compared to experiment 3. Concentration did change 0.1 to 0.2, but temperature also changed from 20 to 40. Now this would mean that actually experiment 1 is not a good reference, because as a reference, each time if you want to compare about the effects of the variable, you should only change one thing. Likewise, if you take experiment 1 as a reference, you compare to experiment 4, you'll notice that yes, the concentration did change, temperature didn't change, but then you actually use a catalyst. So experiment 1 will not be the perfect example to compare to something else. So what do I mean by that? If you take a look at experiment 2 now, if it's experiment 2 and compared to experiment 1, you'll notice that, hey, there's really a change in concentration, but nothing else changed for temperature, nothing else changed for catalyst. So experiment 2 can be used as a reference to compare to experiment 1. Or if you take experiment 2 and you compare to experiment 3, nothing changed for the concentration, temperature is doubled, nothing changed for the catalyst. So experiment 2 can be used to compare with experiment 3 because temperature has changed. Last, if you take experiment 2 and compare to experiment 4, you'll notice that nothing happens to the concentration, nothing happens to the temperature, but this time around there is a new catalyst being added. So there is this one variable that's changing each time when you compare, and therefore experiment 2 is actually the reference. So think of experiment 2 as like the original experiment, and each time when you have to investigate, you either change concentration to get experiment 1, you change temperature to get experiment 3, or you change catalyst to get experiment 4. But number 2 is the OG right? So you start with this original reaction, that is your first one. Right? Later we'll talk about how to explain. Next question, we are supposed to use ideas about collision between particles to explain why changing the conditions shown on the table actually affects the time taken for the black color to appear. Now, recap, whenever a question is talking about collision, we meant frequency of effective collision, right? And of course, in this question, they are linking the frequency of effective collision to the time taken, which is basically something that helps us to understand how fast or how slow the reaction is. Okay, so let's take a look at how to explain 1A first before we go on to talk about 1B as explanation. So for 1A, right, we can explain that actually experiment 2 is the one that's used as a comparison, because whenever you compare to the other experiments, only one variable is changed at the time, like what I mentioned earlier, right? So that is one way to answer about the part A. For part B, right, you'll notice that it's actually 5 marks, right? So 5 marks is a lot, and actually what they want the students to do is to first explain about the effects of concentration. So if I go from 0.2 to 0.1, tell me what happens. Also then compare to tell me about the effects of temperature. If I go from 20 to 40, tell me what happens. Then also tell me about the effects of catalyst. If I go from no catalyst to have catalyst, similarly tell me what happened. Right, so these are actually quite a number of things that you're expected to compare. And likewise, that's why you get a lot of marks for this part. Right, this actually came out in 2021 of the O-level, which is not too long ago, just 4 years ago, right? And you can be expected to write something like this. And that is really a test of how well you can phrase your answer in terms of explanation. So how I'm going to show you this is not the answer, but generally you should know that your answer should capture some of these key points. Firstly, if you're talking about concentration, you need to make sure that your explanation actually covers the concept on number of reactant particles per unit volume. And that's a key concept. Second, if you're talking about temperature, when temperature changes, your answer must cover the concept of linear of kinetic energy, movement of particles, And of course, like what we saw just now at the start of the video, that whole example of how particles actually have energy and how they actually have energy equal or greater to activation energy. Now there will now be more particles with energy greater or equals to activation energy. And if you want to talk about catalysts, that's where you need to link to the fact that actually for catalysts, activation energy is lowered, and then there are now more particles with energy equal or greater than the activation energy. And then all these few answers should link us back to our frequency of effective collision over here. Alright, so what you see over here is that essentially what we are getting the students to think about and to actually describe to us clearly is what happens every time when there is a condition that's been changed. We are not interested for the student to just say that temperature concentration increase means higher frequency of effective collision. We actually want the students to be able to explain to us what exactly is going on, and that's where your marks actually come from, right? In order to secure that 5 marks that you're looking at. Okay, so we have watched a video at the start of this whole explanation talking about what it means when temperature increase, then there are now more particles with energy equal or greater than the activation energy. Now let's take a look at what happens if there's a catalyst and when it lowers the activation energy. What does it really mean when we say that there are now more particles with energy greater or equal to activation energy? So hopefully watching this second video now actually gives you a better sense of why we actually require students to explain or phrase the answer in this manner. Do take note as you're watching a video is try to understand what exactly is happening. Don't memorize the explanation, because usually when students memorize the explanation, that is where they start to write things that is a bit contradicting, and end up they get penalized by themselves because of the way they phrase the thing. So try to understand what we mean by more particles with energy greater or equals to activation energy.
Now, we saw in the last video that catalysts provide an alternative reaction pathway with a lower activation energy. So I'm showing you here the activation energy in the presence of a catalyst, and remember that we abbreviate that as EC. All of the molecules which now have at least this energy can collide effectively and react. And again, I'm representing these molecules by the green area under the curve. As you can see, this is a much greater number of molecules than for the uncatalyzed reaction. And this explains why the rate of reaction increases in the presence of a catalyst.
Alright, hopefully this video gives you a better sense of what the concept is and why are we phrasing in this manner. Alright, let's take a look at the second question, which is, or rather the third question, which is about this concept on limiting reactant. Now, for this question, let me just open up a new page. So over here, what the question is trying to say is that, hey, take a look at the reaction. There's actually a reaction between your iodide as well as your hydrogen peroxide, and this reaction actually go on based on the different volume and concentration that we're looking at. And of course, based on the question itself, we are being told that the volume of hydrogen peroxide used each time is 30 cm3 and is at a concentration of 0.05 mol per dm cube of hydrogen peroxide. And in terms of the iodine, we are also told in the question that each time we use the iodine, we're actually using 10 cm3, right? And then acid is added in for the reaction to happen. Now, what the question is trying to get us to think about. First and foremost, remember that in every mole concept question, you know that this is a mole calculation question now, definitely. And if you read the information, you know that they're actually telling you that there's 30 cm3 of this hydrogen peroxide and is using it at a concentration of 0.05 dm3. As for the iodide, you realize that each time they are using 10 cm3, but in terms of the concentration, you realize that there's actually two concentrations the question is talking about. One is 0.1, the other one is actually 0.2. Right, so it could either be with a concentration of 0.1 mol per dm cube or a concentration of 0.2 mol per dm cube. Right, and then the question wants us to find out that, hey, do you know that whether you can find out whether in the different experiments here, whether iodide is actually a limiting reactant or is hydrogen peroxide the limiting reactant? Now, why is this question a limiting reactant question? And the basis is, question actually gave us all the information that we need about the reactants. They told us that hydrogen peroxide, the volume, the concentration, we can actually find mole. They told us for iodide, the volume as well as the concentration, and we can find mole. A question like this is always about limiting reactant because basically they are giving you all the information and then they are asking you to compare and decide which reactant is the important one. So just a quick recap here, even though this question is not about limiting reactant, you recall that sometime back I always share about this burger making example, right? When you have two buns and you have a patty, how do you then form a burger, for instance, right? Then we mentioned that this is the recipe and how it works. So this question now is using the same concept. They're actually trying to tell you that, hey, I have, for example, 30 of the patty, but I have 10 of the bread. Can you tell me which one is limiting? So as a student, what we do is that we don't just say that, oh, 10 is less, so 10 is limiting. That's not how limiting reactant works. We actually need to look at the ratio, right? Ratio comes from the recipe. So what does the ratio say? The ratio tells us that if you just look at the bun as compared to the patty, we'll know that the ratio is 2:1 based on the recipe. So what it means is that if I have 10 of the bread here, that means I only need 5 of the patty based on the recipe itself. Right? So if I have 10 buns, actually I only need 5 of the patty because the ratio is 2:1. Right? Then I realize that, oh, but I should have 30 of the patty. Hence, the patty is too much, and therefore is what I call in excess, and therefore your bun is limiting, for instance. Right, so that was the example about the sandwich making one. What I want you to understand here is not so much about the example, but the fact that when someone is very kind and give you everything about the chemicals, you need to ask yourself whether is the 10 more important or is the 30 more important. And how do we compare them? We don't just say that, oh, 10 is less, therefore 10 is not enough. Instead, we look at the recipe again and ask ourselves, if now I have 10, how much do I really need for the reaction to be done? And then whether I have too much or too little. Alright, so keep this concept with you because we're now going to take a look at how we apply it to this particular question. So in this question, right, you are being told that there is a certain volume or concentration of hydrogen peroxide. So what you can do first is that you can actually first find out the mole of hydrogen peroxide. In this case, it's 0.0015 mole. Then the question also mentioned that each time we are using the iodide, right, we are using 10 cm³ of it. And we know that the iodide can either be in 0.1 or 0.2 in terms of the concentration. So if you are using a 0.1 mole per dm³ of iodide, this will mean that the mole is actually volume times concentration, which is 0.001 mole. But if you are using a 0.2 mole per dm³, you also mean that you are actually taking the volume of 10 divided by 1000 times 0.2 and end at 0.002 mole. Now this means that actually in the whole reaction, right, either you are using this mole of iodide or you are using this mole of iodide. But the question is this amount limiting or is this amount considered excess already? So is it already too much or actually it's not enough? Then that's why we go back to this hydrogen peroxide. We are given 0.0015 mole of hydrogen peroxide each time. And based on the equation, we know that for every 1 hydrogen peroxide, we need 2 of the iodide. So now, if I have 0.0015 mole of hydrogen peroxide, I will actually need 0.003 mole of iodide. Okay, so I hope you are following so far. Because I work out that this 0.0015, I can say that technically I need 0.003 mole of iodide. But hey, take a look, at the start you only have either 0.001 or 0.002, which is definitely not enough to meet the 0.003. And that's why we can say that because there was only either 0.001 or 0.002, which is not enough, hence iodide is the limiting reactant. Right, so I'm going to zoom out a bit here to just pause for you to think of the corrections. You can pause the video, right, or you can replay the explanation just now to better understand what this limiting reactant is talking about. Alright, then now we'll take a look at the next page of the explanation. Okay, for the next question here, to be fair, this is going to be something that's pretty new to everyone here because this actually has to do with more about transition metals as well as catalysts in terms of what they do. Right, so over here, you can treat this as a database question because they have some information at the start which can help you to answer the questions at the bottom, right? And you can study this chart to see what's going on. Okay, so what happened over here is that they mentioned in this para that this whole thing is using palladium, which is a very expensive metal, and what it does is it's a catalyst, right? What does it do in the catalyst? It actually allows the oxygen and the carbon monoxide to react together. So what happens is that there's this process that's called adsorption that's new to you. Basically, it means that the molecules become attached to your surface. And then what happens based on the reading is that when it's attached, some bonds can be broken and some bonds are brought together to form new bonds. Right? Then in the process, you will form a new product. And then the product will be released after a while. So what we're seeing here in this picture here, right, this diagram, what they're trying to tell us is that at the start, look at the oxygen atoms, right, and the carbon atoms, right. What happens at the start is that this oxygen molecule here gets adsorbed, means that they stick onto the surface, right. Adsorption means attached to surface based on the paragraph above. Right, so what happens is that we see that the oxygen is being attached to the surface, and not only is it being attached to the surface, we also see that there's actually bond broken because the O2 actually become two single oxygen atoms. Then we're going to take a look at stage 2. Stage 2 now shows that the carbon monoxide is adsorbed, which means it attached to the surface, and therefore we say that carbon monoxide adsorbed onto the surface. Stage 3, what we notice is that, hey, there is actually some form of reaction that's happening. In fact, there's actually bond formation whereby the oxygen is bonding to the carbon monoxide, and then that forms your carbon dioxide. So that's why we say that the oxygen atom actually reacts by forming bonds. And then we go on to stage 4. This is basically going from adsorb to releasing. So this is actually a detach of the molecules or release of the molecules as it leaves the whole system. Right, so that's why we say that carbon dioxide detached from the surface and then release. So treat this more as a database question with the information at the top telling you what is the process that's happening, and then you need to try to make sense of the diagram over here. Next, question talk about this being an exothermic reaction. So we know that exo means that enthalpy change is negative, so energy is being released, right? And we're supposed to show a reaction, or rather show the energy profile diagram when there is a catalyst and when there is no catalyst, right? So as per all your usual diagram, you need to take note that the starting and ending point of your reactant and product must stay the same. Okay, so the enthalpy change must always be the same. But what really changes is that mountain. Right, so we mentioned this in the previous question just now. Over here the mountain is a lot higher. Over here the mountain is a lot lower, right? And that's how your EA is actually being affected. Now, so what is activation energy? Just repeat again. You start from where the reactant is. You draw a spike to the peak of the mountain. That is your activation energy. Right, so you draw a line where the reactant is. Draw a spike to your mountain where the activation energy is. Right, and make sure you have all your dotted line here to show working so that people know where your arrows are pointing to. Right, so this question I think generally the class did fine, just need to take note of all these little things and whether you have your dotted line, etc. Right, so what exactly is the effect of a catalyst, right? We have seen this in the video just now. Basically, catalysts, what they do is they provide an alternative pathway with lower activation energy. This then increases the number of particles with energy equal or greater than the activation energy, and therefore the frequency of effective collision increases. So that's actually how a catalyst works. Okay, so this one I think shouldn't be much of an issue. Then move on to the last question over here. Now in this last question, you'll notice that the reaction is between copper 2 carbonate with dilute acid. So we know that the reaction is actually copper 2 carbonate plus, in this case, experiment 4. So if you focus on experiment 4 only, it's copper 2 carbonate plus nitric acid. This should form copper 2 nitrate, carbon dioxide with water, right? So the formula of the salt form is definitely CuNO32. Okay, so a student carry out 3 experiments using acid at room temperature and 1 experiment using acid at a higher temperature. So you're supposed to look at this set of data and see for yourself which is the experiment that involves the higher temperature. So likewise, most of the class actually did quite well because you were able to see the data, right? We have 4 experiments here. In order to know which one has the different in terms of temperature, we need to take note that we can't be comparing 0.5 with 1.0 because this is about different concentration. We can't be comparing hydrochloric acid to nitric acid because these are about different acids. So actually what we need to compare is to compare experiment 1, which is hydrochloric acid is 0.5 mole per dm cube, with experiment 3, which is also hydrochloric acid, also with 0.5 mole per dm cube. And we'll notice that the time taken is actually different. So the time taken for experiment 3 is shorter as compared to experiment 1. And now this would mean that experiment 3 is likely to have taken place at a higher temperature. The reason is because even though experiment 3 uses the same type of acid, which is hydrochloric acid, same concentration, which is 0.5 mol per dm cube as experiment 1, the time it took for the collection of 10 cm3 of gas was actually shorter at 7 seconds, and therefore we can conclude that it's actually faster due to the higher temperature. And this is because the question say that, hey, one of it is a higher temp, right? And that's why we deduce from there. Alright, and then we take a look at B part 2. Similarly, question is asking you to explain in terms of collision. This means our concept of frequency of effective collision must come in, right? And we talk about temperature, and that's why we need to talk about the number of particles with energy greater or equals to the activation energy, right? And therefore the last part, the answers will be as follow over here, right? So when temperature is high, particles gain kinetic energy and move faster. As a result, there are more particles with energy greater or equal to activation energy, and this increases the frequency of effective collision, which then increases the rate of reaction. Alright, and with that, we have come to this part to conclude the structured question component, and now we'll work back to see the MCQ questions. We only will go through a few MCQ questions which are a bit tougher, but the rest of the questions we can address it when we go back to class. Alright, now coming back to the MCQ, right? The MCQ's answers for the 10 questions are shown over here on the screen, as you can see at the top over here. Now, in terms of questions that I'll be going through, there's only 3 questions that I have in mind, right? The rest of the questions we can actually talk about it during consultation or back in class, right? So the first question that I want to address is actually on the second page, question 3, right? So let's take a while to process the question. We'll read through and underline together. Now, remember that every question about rate of reaction, there is information about what exactly is excess and what exactly is about limiting, right? And that's where, as students, you need to read carefully and take note of the phrasing. So for question 3, you read here, you realize that there is this excess chemical here, which is the acid. Now, I mentioned to the class before that in every graph question, there's always a how fast and there's going to be a how much. Now, what do I mean by that? A how fast question is something that addresses the gradient of the graph, whether the gradient is going to be steep or whether the gradient is going to be gentle, right? So that's about the gradient of the graph. A how much question is about the height of the graph. That means how much of the product you're going to get, right? So a how fast question is always affected by 5 things: concentration, temperature, pressure, size, and whether there's a catalyst. And it doesn't matter whether you are affecting the limiting reactant or the excess chemicals. So based on this question, we know that magnesium ribbon is limiting, whereas the hydrochloric acid is excess. So that's a how fast question that we need to answer eventually if we are looking at there being a change in terms of con, temperature, pressure, size, or catalyst. Now, a how much question will only affect if there's a change in mole of limiting reactant. Why only limiting but not excess? Because we know that excess chemicals actually doesn't affect the amount of product. It's the limiting reactant that affects the amount of product. So let's look at the question here. So which graph will be produced when 0.5 grams of magnesium ribbon, which is a limiting, is now reacted with an excess of 2.0 mol per dm cube of hydrochloric acid under the same condition. So first and foremost, we know that what's the difference? What actually changed? What changed was the concentration of the acid. It went from 1 to 2. So there's an increase in concentration. Therefore, this should cause it to be faster because concentration increased. Number of reactant particles per unit volume increased. Frequency of effective collision should increase. Now, but the amount of product will still be same. Why is the same? Because you can change the hydrochloric acid, but the hydrochloric acid is in excess. Therefore, it will not affect the how much. So in this question here, how fast is being affected, but how much actually stays the same. So if the initial graph is graph 1, we know that it's faster, right? That's why we have actually look at graph B being a faster graph. The gradient will be steeper, but in terms of product, you will actually stay at the same height as graph 1. Okay, so I'm quite happy to see that as a marking through, actually most of you are able to score for this thing, which is a good one. Right, so that's for question 3. Then let's move on to talk about question 4. Right, both are on the same page. Now question 4 is a bit different here now because the question actually didn't say excess or limiting. If you read the question, you realize that you can't figure out what's excess and what's limiting. And then you might be a bit uncomfortable to see whether you know whether there's a change in terms of the height. Okay, but not to worry, you'll realize that actually if you count the mole of the hydrochloric acid, the mole over here is equivalent to volume times concentration, which in this case is 0.1 mole. And if you work out the second part here, the mole is also volume times concentration, which is equivalent to also the same amount of mole. So what this means is that actually it doesn't matter because both of the hydrochloric acid was actually the same, and both of the magnesium has always been the same. It has always been 1.2 gram. So actually in this whole question here, we know that the how much will never change. Right? So remember, every question there's a how fast and there's a how much. And in this question here, how much is actually not important anymore because there was no change in terms of the mole of the chemicals that you're playing around with. Okay, then let's take a look at whether how fast it changes. So is there a change in concentration? We read through and we realize that, hey, there is a change from 1 mole per dm cube to a 2 mole per dm cube. Right, so based on our understanding, when it's 2 mole per dm cube, it must be faster. Why? Because there's now more reactant particles per unit volume, high frequency of effective collision, faster rate of reaction. Okay, so first and foremost, A is out because it shows that it's different, how much is different. C is out because the height is different. So we're looking at B and D. And then we ask ourselves which one is actually faster. And we'll know that actually experiment 2 should be faster because of the fact that it's using 2 mole per dm cube of hydrochloric acid. And therefore the answer is actually option D. Right? Just to repeat again, the how much is the same because you're using the same mole throughout all the changes that's happening. Alright, so I think these two MCQs are quite good at helping to test whether you are very clear about your concept on how fast and how much whenever you're changing any of the conditions. So let's take a look at another question now, and we can zoom in straight to question 7. Right, so question 7 is one of the other questions that quite a lot of students have issues with. And we'll take a look at this. So based on this question, we know that 1 mole of X reacts with 1 mole of Y to produce a gas. So X to Y in terms of ratio is 1:1. A student then investigates the reaction by measuring the volume of gas produced at regular time intervals, plots the whole thing, and then he figures out this whole graph. So you look at graph R and you look at graph U. Right? You realize that in terms of speed, graph U is faster. But same amount of product. Right? Which means that in terms of the mole, actually there wasn't a change in terms of the mole. Right? So I think we keep that in mind first, then later we're going to figure out what exactly is happening here. Okay? So in order for graph U to be faster, it means that in terms of the condition that's changing here, there must be a change in, or rather not just change, there should be a increase in concentration of either X or Y, right? If not, it shouldn't become faster because this question is all about concentration, right? So we take a look at the option here. Those with the drop in concentration, like option 4, is definitely out already because the concentration fell, right? Option C is also out because while the concentration for X is still 1, the concentration for Y actually dropped, right? So it shouldn't be the case, right? So it shouldn't drop in terms of concentration because dropping concentration will actually slow down the reaction. Now, but what about A and B? How do we know whether should we have more or less and what exactly is happening? Because it looks like there is a change in terms of concentration. And now we need to look at, so we know that it will be faster because the concentration changes. But now we need to look at this second part of the graph, whether the same amount of product actually comes out. That's where we actually have to zoom in and calculate the mole of the chemical. So for X, if you look at this whole thing, right, if you have 25 cm cube, and then you have, so you go with option A, so we calculate each of the mole in terms of the X as well as the Y. Right, so first is if you have 25 cm cube, you have 2 mole per dm cube in terms of concentration, your mole will be 25 over 1000, multiplied by 2, and that will be 0.05 mole of the chemical. Then if you have 100 cm cube, multiplied by 1 mole per dm cube, your mole will be 0.1 mole of chemicals. And let's take a look at the right hand side. If you have 100 cm cube here, your concentration is 1 for the Y. You are looking at 0.1 mole in terms of the molarity. And then go on to the next one. If you are looking at 50 cm cube, you multiply by 2, it will give you 0.1 mole of the chemical. So now you take this and you compare back to the original reaction, which is the one that gives you graph R. You realize that for graph R to happen, the X here was actually 100 cm cube times 1, and this will be 0.1 mole per dm cube. Sorry, 0.1 mole. Same over here, it's about 100 cm cube times 1, and this will actually be 0.1 mole of the molarity. So what this means is that actually for graph R, right, what must happen is that there must be 0.1 mole, there must be 0.1 mole of X and Y. Now, given that graph U is the same, right, then we also want a case whereby you have 0.1 mole and 0.1 mole of X and Y. And that's actually how we derive the answer as option B, right? Option A cannot because the mole of X is too little, it's only 0.05. And that's where option A is actually strike out over here. Okay, this question is not that easy. If you still have certain questions understanding about what this means, right, we can go through this back in class. Yep. So with that, we have actually come to the end of this entire video to explain about topic 15, right? If you have any questions, feel free to approach the teachers. If not, you can take some time to look through the answer key as well as to watch the video again to clarify. Thank you.